things I'm given into things I need for my poset. And next I'll check that the rules I'm given, A and B, are going to turn into the rules I need for a poset, namely the reflexive and the transitive law. Yeah.
So if I'm understanding correctly, B is just like the triangle rule on steroids.
Yes.
Okay.
Yes. It's the generalization of the triangle inequality from metric spaces. Yep. Which we'll see soon. So
your identity morphism, do you interpret it into as giving you always a group or
given you always, oh, so you want to say what A is. So A, I think you're saying, is that true is less than or equal to XPP. In other words, XPP is either true or false, but true is not less than false. False is less than true. So if this holds, then that means i.e. P is less than P. So the identity axiom is turning into the reflexive law for posets. Is that what you meant to ask? Yep.
One thing that's confusing here is that there are two posets hanging around.
There's
the poset bull, and then there's poset arising from this category.
Yep.
So the first inequality here is in the poset bull, and the second one is in the category, the poset
okay, I'll
we're
put this
constructing.
one in that shape. Okay. So here, the quote thing is our interpretation of these structures and these axioms. So we just proved using A that P is less than or equal to P, and using B, we get that XPQ and, because that's the monoidal structure of bool, if P is less than Q and Q is less than R, then P is less than R. So the only way this thing has any force, if this thing was false, if the left-hand side was false, then this axiom would tell us nothing. So the only time it has any force is if the left-hand side is true. And that's only true if both of these two are true. So what this really says is if P is less than Q and Q is less than R, then implies P is less than R. So a bool enriched category is a poset. For every two elements, you get a yes/no instead of a set of things. Okay, now let's talk about metric spaces. So I don't assume you know what a metric space is. So the definition.
2 minutes ahead of schedule if you want to take questions.
I'm ahead of schedule.
Yeah.
Any questions? Okay. I will ask at any time, and yeah.
I still fail to see where the morphisms are that allowed you to call X a category to
Enriched.
start with.
Yeah, it really should be
You
called.
said you started with a category that was not enriched, and then so where is that category?
Okay, no, it's really not a category enrichment. It's not a category that we did something extra to, which is what enrichment sounds like,
Yes, that's
right?
what it sounds like.
It sounds like you had this thing and then you made it better. So we
Yeah.
must have had a category and then we made it even better.
Uh-huh.
And that's misleading. So maybe B category is the right answer. So it came from situations where it wasn't misleading, where instead of having a set of elements, you had a vector space of elements, which is a set plus structure. Or instead of having instead of a set of morphisms, you have a vector space of morphisms, or a topological space of morphisms, or a group of morphisms. And all of those are cases of this. But because we've gone down one level and are using posets rather than more complicated categories, our enrichment is, you send your kid to a school that enriches them, and it's just not a good school. It's really terrible.
What you're saying is
that could happen, and we are doing that.
So what you're saying is before you send your kid to school, they're not really a kid.
Right. Okay. Okay. So I think what your comment is making me think is that this is a better term, V category.
Okay.
V comes before category, telling you I'm changing what I mean by category. It's a V category, not just a category.
And
So
if you looked at the resulting poset as a category, it would be the same thing.
if you look at the
monotone maps of isomorphisms, all that stuff.
I think so.
Yeah. Okay.
Okay. So, oh right. So if you, yeah, we could also be talking about enriched functors.
Right.
We could be talking about enriched natural transformations and all sorts of other things. And the enriched functors, the Boole enriched functors between Boole enriched categories will be the poset morphisms, the monotone maps between posets. So it'll recover all the original ideas about posets. So the definition of a metric space is, a metric space is, consists of, one, a set X called the points. Elements are called points. And a function d that takes two x's and gives you a real number that's at least 0, called the distance. So you can already see something like what's going on up there. But it has to satisfy 4 rules. A, that d of x equals 0 for all x. B, that if d of xy equals 0, then x equals y. C, d of xy equals d of yx. And D, the distance from x to y plus the distance from y to z is bigger than or equal to the distance from x to z. This one's called the Triangle Inequality, which someone mentioned. And unfortunately, categories enriched in LOV are not metric spaces. That's unfortunate because metric spaces are the classical notion and an important idea. And we don't recover that. We could recover something else that I actually think is better looking back on it. And that is that I think these two conditions you don't really need. And why not? So imagine that metric spaces, so the idea of metric spaces is you want to get from here to there, and you take the minimum distance, like you take the root, you take the shortest route, I guess I'll use the other word, and with that, and you get this triangle inequality, and it satisfies all these things. So the distance from here to here is 0. If the distance from A to B is 0, then A equals B, all sorts of stuff like that. But it almost works if you, instead of thinking about distance, what if you think about effort? Which actually might be more important. So there's a distance from here to Pakistan, but there's also the effort of getting from here to Pakistan. And those are different. So if you have the effort from getting from here to there, there's no real reason that should equal the effort from getting from there to here. Right? It's easier to get downhill than it is to get uphill. So that requirement I don't think is all that useful or necessary. It's something that you could have, then you have a better metric space or something, but it's not. So if you think about effort, you get the first one, the effort of being where you are is 0, effort required. And if you can get from here to there, from x to y, and from y to z, then certainly, if you take the minimum distance from x to y and the minimum distance or effort from y to z, that's bigger than the minimum effort from x to z. But you also don't have, what else? The effort from uphill to downhill might be 0, does not imply that x and y are the same point. So if the effort is 0, it doesn't mean you get that x and y are the same. So I'm questioning B, I guess, and C. Maybe they were C and B. And if you drop B and C, then you get Levere metric spaces. You could also imagine enriching in a category where you allow infinite distances or not. Like, do your metric spaces allow for infinite distances or not? Sorry, I'm kind of rambling here. So let me write down LOV again. Lob is this category where the monoidal poset, 0, infinity. You could use R if you want. You could use just 0 through non-infinity. Where the ordering is this one. The monoidal unit is 0, and the monoidal product is plus. And so what is a category? What is a Lov category? A category enriched in Lov. But we're calling it a Lov category after the objection, which I think is a good one. A Lov category is 1, a set X. Let's call it X. 2 for a function of x, well, x times x to r greater than or equal to 0 or infinity, whatever. And let's call that distance. Such that 1a 0 is greater than or equal to the distance from x to x. But the distance from x to x is also less than or equal to 0 because that's the smallest possible thing. So if it's bigger than, so if 0 is bigger than this, in other words, that's the same thing as saying d of xx equals 0. And b, the triangle inequality, says that d of xy plus d of yz is greater than or equal to, which is why it's important we switch the sign. We would have gotten the wrong thing otherwise. Right? We switched the order from the usual one. And that makes it so it works. If you use the other order, this would still be a nodal poset, and you'd get some kind of weird backwards kind of thing, which would no one's found a use for until you. And so this recovers what's called, this is called a Levier metric space. So these are much more useful in my opinion because, for example, you could take the space, you could take the world, and you could take whole regions of the world instead of points. So you could have Boston and the U.S. and China, and you could say that the distance from one point to one region to another was like, if you need to get just any, you're in the U.S. and you need to get somewhere in China, how long does it take? Well, the distance from the U.S. to Boston is, whatever your worst case scenario in the U.S. is, you need to get to Boston. It could be huge, but your distance from Boston to the U.S. is 0. You're already there. So it kind of makes, someone says, like when you think about getting somewhere, like let's get to Cambridge or let's get to MIT, if you there is a sense in which you're already in Cambridge, but you need to get to MIT, and this is a Levier metric space, but it's not a regular old metric space, and I think it's a useful concept. But my main point is to say that when we enrich in one of these monoidal posets, we get interesting things back. Let me give you some examples of Levier metric spaces, where you can get them from. So I already said some things about regions of the U.S. or whatever. But there's also just drawing graphs. So if you draw a weighted graph, then from this will create a Levier metric space. So these are kind of like one-way roads and how long the roads are. And so if you have A, B, and C, then you could make a table of distances. You want to go from this one to that one. Takes you 0 to get from A to A. Takes you 3 to get from A to B. Takes you 5 to get from A to C. Takes you from B to A. So what's the distance from B to A?
9.
Infinity, yeah. Okay, from B to B is 0. From B to C? 4. And from C to A?
Infinity.
And C to B? Okay. And 0. Okay. So when you have Yeah. So I guess I might have done.
So
Yeah.
As in, are you done in according to the material?
Yeah, I think I'm done according.
Basically, if you wanna,
So yeah, someone has a question. Two people have a question.
you're forbid. You don't allow negative. Okay, yeah, you start at 0 because you can't circle.
I'm trying to figure out whether there's a reasonable functor from law of categories to bool categories by saying, like, if you're traveling on a budget, you can make trips
Oh, okay,
that are
so you have
under
0
certain
infinity.
I'm not sure if that works.
And you want to threshold it to 0, 1.
Doesn't composition will be a problem?
So we're hearing that composition will be a problem. So I know I can do this. So here's 2 ways to do it. So let f of a be 0 if a is 0 and 1. Oh, sorry, false true. So if the distance is 0, I can do it. And if the distance is not 0, whoa, what happened? Okay, if the distance is 0, I can do it. And if the distance is not 0, I can't do it. So that's a threshold.
that's when your budget is 0.
That's when your budget is 0. I know that works. And 2, your budget is just anything finite. True if a is less than 0, infinity, and false if a equals infinity.
But you need the pre-image of true to be closed under addition.
Is that
I
right?
think that's the right way to say it.
Okay.
But maybe that's an
Why is that
exercise.
right?
Because, what are you?
So
you want
so
this
to-
map to be a map of monoidal posets, right?
Yeah, so we haven't said what a map of monoidal posets is. But whenever you have a map of monoidal posets, you can take anything enriched in the first one and get something enriched in the second one. Right. I see why. Right, so you have some root 3 and 4 and your threshold is 5. So you can do this one and you can do this one, but you can't do that one. So yeah, I guess you're right. The preimage of true needs to be closed under addition. But I think the real rule is whatever the rules of monoidal poset maps are. And these 2 will satisfy those 2 rules. So you can take any poset, which is a bool enriched category, and get a law of enriched category by taking your poset, your Hasse diagram, and whenever you have an arrow, putting 0, and whenever you don't have an arrow, putting nothing. And then you can go that way. You can also go back. Okay, other questions? Yeah.
I hope this isn't too far afield, but the Hausdorff distance,
Oh yeah, you can do that.
you usually would make it a metric by symmetrizing it, by taking the
Oh, right,
maximum,
right.
either doing
But you wouldn't, in the Levier version, so the Hausdorff distance is, you have
So
some
if you don't
metrics.
symmetrize, I think you get a Levier metric space.
Right,
Yeah.
you get a Levier metric. So Hausdorff distance, you have some metric space, maybe it's R2, and you take subsets of that distance. And that's what I was talking about with the Boston and US thing.
Mhm.
So you have 2 sets, you have 2 subsets of this thing, and you ask what's the distance from this one to this one. And the distance is the Hausdorff distance. So you have A and B are subsets of your metric space. And the distance from A to B is defined to be the supremum over all A and A of the infimum over all B and B of the distance from A to B. What that says is, you're starting in A, you're getting into B. Wherever you are in A, just get to the closest possible point in B. So I just need to get from here into B anywhere I want, any way I want. But I take the worst case scenario over all of A. And so the distance from A to B here would be like that distance. It's the worst case scenario. You're somewhere in A, you don't know where, so it's the worst possible point of A, but you just need to get anywhere in B. So you're in Boston, you need to get to Cambridge. You're in Boston metro area. This is not a metric space in the usual sense, so what they do is they symmetrize it. They say the distance from B to A, I'm just going to force it to be whichever one's bigger between A and B and B and A. But you naturally can take any Levier metric space and symmetrize it. What you can't do is take a symmetric one and get your Levier one back. So it's kind of better to just stick with, in my opinion, to stick with the actual distance, from Boston to Cambridge to be different than the different distance from Cambridge to Boston metro area. And you can recover the Hausdorff distance if you have enough structure on your symmetric monoidal poset. What I mean is, if you take log and you notice that it has all joins and meets, meaning you have supremums and infimums, so you can write these things. If you have any monoidal poset with joins and meets, like bool or anything else, you can define a notion of Hausdorff distance for the V enriched categories. So let me give some other examples, because I have a few minutes left. So you could enrich in take any set M, then P of M is a monoidal poset. So this is the power set of M. Set of subsets. So your elements are, so now your diagrams are going to look like, let's say, sorry, I'm all over this thing here. M is, say, modes of transportation like car, bike, foot. And you write car, foot as the modes of transportation you can use to get you all the way from A to B. And you say, well, from here to here I can get there on foot, and from here to here I can get there by bike. Then if you use this thing, the power set of M, subset, all of M as your monoidal unit, and intersection, then you'll get something where it'll take paths and say well, I can get to here and to here by car and foot, and from here to here by foot, so I can get all the way here by foot. And I can get all the way here by bike. So the actual distance from here to here, instead of being a number, it's this foot comma bike. Those are the ways I can get from A to B. This guy will have all joins and meets, so you can define some kind of Hausdorff distance here, although I haven't worked out what that is. Okay, maybe why don't you talk amongst yourselves and see if you can find a question or an interesting thing, and then we'll discuss it. Or anyone have any questions that they just want to ask? Yeah.
Oh, well, I was
Oh,
wondering.
were you waiting on a question?
No, but
Okay.
if anybody else has something, I was wondering if you could talk more about the set enriched category, i.e. the category.
Okay, sure. So that's what we're going to talk about next time, but let's do it now. So a monoidal category. Anyone else have a question before we move on? Is it okay to move on? So a monoidal category consists of, should I define this? Yes, so it's V. So it's got objects. It's got two, it's got what? Oh, it's a category. It's a category. Together with one, an object I, and two, a functor from V times V to V, called tensor. Before we had an element of our set V, and we had a function from V times V to V that was monotonic. That was what condition A
Is
said.
that taking two V's or the product of V's?
It takes in two V's and gives you a V. Such that satisfying some rules. Like tensor is associative, I tensor anything is the thing, stuff like that. Some things that you might be getting used to. Then you can define a category. Oh, and so an example of a monoidal category is set, the category of sets, where the monoidal unit is a set with one element. You can call the one element 1. That's the object in set that is going to be the monoidal unit. And times, the product of two sets is a set. And if I have a function from, this is a functor, but that's not too important. The product of two sets is a set. And a category enriched in V, which I guess we'll call a V category, consists of one, a set ob x, 2, a function x taking ob x times ob x to v. So this says, this is going to be like the Hom set. For every object and object, I have the set of maps from that one to that one. V is now sets. So instead of landing in just some poset, like the numbers, I get a set of maps.
So maybe ob3 is slightly better.
Ob3.
What is the 1 inside the unit of that monoidal category?
This is a set with one element, so I could call that thing, you can call it whatever you want. It's a set with one element that you're going to just fix for all time as your monoidal unit.
So, is it all of the possible single element sets,
No,
or is it just one?
Oh, sorry, it's a monoidal structure, which means you picked one.
Okay.
What is the time set?
This times?
Yeah.
This one is just the name of a weird shape I made. This one is that I can take any two sets, 1, 2, A, B, C, and form the product set. 1A, 1, 2A, 1B, 2B, etc. So it's just a product. So the monoidal product for sets is the product of sets. Yep.
So you won't have stuff like I tensor I is I.
You do. Those are the rules. I said
Okay,
satisfying
but
some
you can
rules.
have additional stuff.
So
Okay.
you have I tensor, any set A is A, and A is isomorphic to any A tensor I, and A tensor B tensor C is A tensor B tensor C. Those are the rules.
But how does that example satisfy that rule? If my identity is the set containing only smiley,
Yeah.
and the ordered pair smiley comma A is not the same thing as A.
Right, but it's isomorphic to it. So if I take my set 1, 2, and I product with smiley, then I get the set 1 smiley, 2 smiley. But that will always be isomorphic in an obvious way, like a way you can write down once and for all, with the original 1, 2 set. So these 3 rules will always hold. There will be an isomorphism, and in fact, those isomorphisms will work together in a nice way that I'm not writing down here. Yeah.
So this is like groups, but not all the elements have to be of the same type. Kind of. It's like a generalized
exactly.
group.
It's a
Okay.
a category is a generalized group. So you have the group of all n by n matrices that are invertible. You have the monoid of all n by n matrices that aren't necessarily invertible. That means you don't have inverses. And you have the category of all m by n matrices, where when you shoot over to another one, you've left, you can't multiply m by n again, right? And so you have to multiply m by n by p.
But that's just a category. A monoidal category puts another monoid, a binary operation
Yeah.
on
Maybe he's
everything.
here. He's a category enriched in.
In set. Okay.
So a category enriched in set has for every two things a set of matrices, m by n matrices or whatever.
Yeah, that's a good one.
Plus some other
Categories are
stuff.
generalized groups.
Okay, so I think that's time. So thanks.
We'll also say a lot more
And
about
I'm
this
here.
next week.
Yeah, we'll say more about this on Thursday.
Oh, sorry, Thursday. Yeah.
On Thursday, and I'm here if you have questions. So yeah.